Welcome. Today I'm going to be showing you how to fit a linear regression model in the R programming language. I'm going to be using built-in functionality as well as a built-in data set to do this. And again, this will be a very simple introduction. I won't be talking about the theory very much, simply how you execute it in R, how you fit the parameters, and then how you interpret the output that R gives you. So with that in mind, we're starting here with an RMD file. If you don't know how to use an R Markdown file, I'd invite you to have a look at some of my other videos on this channel where I go over an introduction to RMD files. So to begin with, we will use a built-in data set which is called mtcars. So mtcars is a data set which is included with every installation of R. And because it's a built-in data set, we just use the data command to access it. And you'll notice that mtcars is now under the environment. If you would like to know some information about mtcars, or really any data set that's built in R, you can just use the question mark for help, mtcars, and what you have here is all the information about it. So this was data that was extracted from the 1974 Motor Trend US magazine. It's 32 automobiles. There are 11 different variables, and they're all numeric. There's footnotes, as well as some information there about it. And you can do that with just about any built-in data set. It'll give you that information about it. So let's go ahead and we'll just create this as a data frame. And I'll just call this a data frame MC. Maybe I'll do it MTC for Motor Trend Cars. And then we'll just print out a few of the observations, maybe the first 5 observations, just to have a look at them. So here we see you've got the RX4. It's got miles per gallon. It's got number of cylinders, the displacement, horsepower, other things that we'll need to look up at. So we have horsepower, the rear axle ratio, which is DRAT, weight in thousands of pounds. So a Mazda RX-4 weighs 2.6 thousand pounds. How long it takes to do the quarter second or quarter mile, how many seconds it can do the quarter mile in. The engine, whether it's a V or an inline engine. Transmission is coded as being 0 if it's on automatic, 1 if it's a manual. Number of gears and number of carburetors. So let's build a model. And in our case, suppose we're interested in what's the relationship between horsepower and quarter second, or how long it takes someone to do, or how long it takes a car to do a quarter mile, how many seconds. So that's the model that we're going to build. So our dependent variable is going to be q sec, so number of seconds it takes to do the quarter mile, and our independent variable is going to be horsepower. So that's the model we're going to build. Let's do another code chunk, and we'll just make some commentary. In this case, we'll say build a linear regression model to quantify the relationship between horsepower and quarter mile time. So we're going to create a model we're going to call this model something. So I'm going to create an object. The advantage of creating an object as opposed to just getting the output is once we have the object, there's a number of interesting things that we can do with it. But before we do anything else, let's just have a look and see what the relationship looks like visually between horsepower and how long it takes to do the quarter mile. Again, this is just a standard scatter plot. We're using base R. We are not using ggplot or other things because we just want to get a quick idea. If you don't know how to do this, perhaps I'll make other videos on how to do this. Oh, and I made a mistake. That's right. What I needed to do was actually specify where this data is coming from. In this case, the data frame, the MTC. There we go. So what we see here is there seems to be a negative correlation. In other words, as horsepower increases, the time it takes to do the quarter second seems to be decreasing. Let's clean up this plot a little bit so it looks a little bit nicer. Let's choose the X label, and we'll say the X label is horsepower. The Y label is time to do a quarter mile. And for those of you who don't know, quarter mile is the standard distance at a drag race. All right. So let's see how that looks. Yeah, that looks a little bit better, a little more descriptive. And finally, let's just change up what these individual markers look like to do something that's going to stand out a little bit better. Okay, and we'll just, again, we'll change the marker type PCH. Marker type 20, I think, will give us black circles. Do I need to rerun something? I think I might. There we go. There we go. So yeah, we can definitely see that there seems to be a negative correlation there. So let's go ahead and actually calculate what that is as well. Let's calculate the correlation coefficient to see what that relationship looks like. So we will do that correlation because we don't know precisely what the distribution of these two variables are. We'll use Spearman's correlation. So we'll just do core. We'll grab horsepower and the quarter second, which is what we're interested in. And I believe its method equals Spearman. So what we see is that, yeah, so there's a negative correlation, which means that as the one variable increases, the other decreases. So that's something that we're familiar with. And in this case, it is negative 6.6. So, you know, that's a moderately strong correlation, negative correlation between the two, which again is exactly what we'd expect to see. Well, we will end this video here at this point. We'll come back and we will look at how to build a linear model using this data. So again, we'll be using horsepower as our independent variable, and we'll be using time to do a quarter mile as our dependent variable. So hope to see you at that next video.